Good morning. Okay. Yesterday we have seen Griffith's experiment. Right? We have seen that how Griffith has managed to do with his pneumococci, right? And then he could show that eventually that DNA is the genetic material. However, right, followed by Griffith, Avery, McCarthy, McLeod, three people, they were biochemists as I explained you. They also showed that okay, by enzymatic digestion and all, like the genetic material is final eventually. But the enzyme digestion is never perfect, right? So it is like always has an iota of doubt into it, right? So people they were like okay, they accepted more and largely, but then there were some doubt about like what the experimental results were. So the experiment further design was by Hershey and Chase, right? Hershey and Chase, Alfred Hershey and Martha Chase, right? So two people came together. 1952, they did this experiment, right? It's like when I will explain you this experiment, what you have to appreciate that this is a very clever experiment, right? Choice, right? What you have to know like what experiment is and how really this experiment is going to get executed. Right, so Martha and Hershey, they have their choice of the experimental system was impeccable. What they choose is bacteriophage. I'm sure you know bacteriophage. It's a virus that affects bacteria, E. coli especially, and those bacteria which affects E. coli, right? The viruses are very simple system. There are only two components, protein code and DNA. So no RNA, no carbohydrate, no lipid. That's why I say it's very clever choice. Right? So to begin with, you have only just two players in it. Either it is protein or it must be DNA. Right? And then it is very easy to maintain. Right? You just have to take a few ml of bacterial culture and then add just phages into it, and these phages would infect. So what they did is further, right? What they do, they have some knowledge about the chemistry, of course, and then what they did is they radio labeled this protein as well as DNA. Now here also their choice is very clear. What they did is they use sulfur as a radioactive material to radio label protein code. There is no sulfur in DNA, remember. Right, and then they use phosphorus, right, to radio label, radioactive phosphorus to radio label DNA. Now, phosphorus is not found in amino acids, right, not in proteins. So that's a very clever choice also, right. So what they did is, how they managed to do that, they grew this bacterial colony into a radio label phosphorus containing medium, right. For many generations, this bacteria also got lots of this radio-labeled phosphorus, and then they infected this bacteria with the bacteriophages. Now what this bacteriophage will do? It will grow, of course, and then when it will grow, it will take up this radio-labeled phosphorus and incorporate into it. Now where the phosphorus will go? In DNA, because DNA has the nitrogen bases and the phosphate sugar phosphate backbone. Right, so phosphorus went into the backbone of the DNA. So your DNA has got radio label, right? And now another set of experiment. What they did is they grew this E. coli with sulfur, which is radio label sulfur, right? And then infected this with phages. Now all those progeny phages that developed, right? They took up all this radio label sulfur, right? And then it went into the code. So you have got two P4 phases, P2 phases they use, P2 phases, right? One has the radio label code, one has radio label code, right? Right. Now what they did is very simple experiment. They allow this phages to infect fresh people, right? And then these bacteria, how it happens, you know that, you have studied it. So this is E. coli cell. Now what will happen is this phage will bind to it, right? these are like tail fibers, this is contractile neck, and inside there is the DNA. Right? Now what will happen when they infect? They will infect this contractile tail will collapse, right? So it will come and the DNA is done inside the cell. So bacteriophage infect every E. coli or bacterial cell by injecting their DNA into it. Right? And now what happens is, this is protein. Capsid is made up of protein that remains outside the cell. Adhere to it, right? But outside the cell. So what they did is, Hershey and Chase, right? What they did, they took just a blender, right? घर में जो मिक्सी होता है ना, so they brought that mixie into it, put this culture into that and blended it. Now what will happen? That's why this experiment is called also a blender experiment, right? So when they did that, what will happen? This will dissociate and this will go off, right? And E. coli will get separated, right? To dissociate this bacterial cell and the bacteriophage, they use a blender, right? Just a mixing, right? And then a kitchen blender they use, and then they agitated this very heavily because of the blender. So what happened? This came off, right? And when this came off, then they centrifuged it. So when you centrifuge, what will happen? The heavy things will sediment, right? So E. coli obviously is heavier, so it will sediment, right? And this will float into supernatant. So two things that they did, right? What they did, right? They allow this bacteriophage, a fresh bacteriophage to infect. Right? Now this bacteriophage is not labeled, but however this is labeled. So you have two sets of experiments, right? The same experiment where there is another phage which is this is protein codes labeled, and this is with phosphorus, right? So now the same thing will happen here also, right? This is the bacteriophage that has infected, injected this, right? Now what is happening? They blend it, broken this off, so you have radiolabel thing into, and then when you centrifuge, right? When you centrifuge that in a tube, you have got E. coli that is pelleted here, and then the bacteriophage particles are floating here. And now they check this thing. What will happen? You will find that all that sulfur label is here in supernatant. Right? That means what? The bacteriophage protein is separated from the E. coli. And this contains DNA. Now DNA inside the E. coli now, right? Because of the infection. So now what will happen? The phosphorus label is here into the supernatant. Right? What they found? They segregate, right? So sulfur label sulfur is into supernatant, and then that shows that there is a good separation in it. Now what they do is they allow this E. coli to grow, right, and produce new phages because these E. coli are infected, right? So what will happen to these phages? These E. coli, they will produce a lot of progeny phages, right? And once they produce progeny phase, that means their life cycle is completed, right? So if their life cycle is completed, so they produce lots of progeny phases, that means, right, their life cycle has been completed here. What does that mean? Right? What does that mean is, it must be the DNA that is being allowing this E. coli to produce the progeny phases, right? Because protein anyway got separated. Had protein been a genetic material, right? If protein is a genetic material, what will happen? Then they would not be produced progeny phases because protein is separated, right? So what they got is DNA, and only DNA can be able to produce the progeny phases, right? The progeny phases will not be able to produce because E. coli will not produce any progeny phases unless and until you have a viral DNA, right? So that is where it showed that beyond doubt now that the genetic material is basically a DNA. Understood this experiment now, right? What they did, right? You have got phospholipid and sulfur labeled phases, right? Allow them to infect, right? Then blend it. So what will happen? They will break the phase particle association with it, and they confirm that their experiment went very well by finding out that sulfur label is up into the supernatant and the phosphorus label is down into the E. coli, right? And then this E. coli, if it produces progeny phases, that shows that the genetic material is only with DNA. So this DNA, which is being injected into E. coli, can alone be able to form progeny phases. Right? So that is where the Hershey and Chase experiment shows. Right? Now, understanding chronology. Right? You know that we talked about Griffith's experiment, right? And then the Griffith experiment shows that there is a factor. Griffith never knew anything about DNA, right? Never confused, right? Griffith only said transforming factor, not transforming principle. So he never knew that there was anything called as DNA there, right? So he never knew, right? So he never said anything on DNA, right? Only thing he said that there is a transforming factor or transforming principle. Okay, it is then Avery, McCarthy and McLeod, they came up, showed that enzymatic digestion, right? They digested one by one, right? Once protein, once DNA, once the lipid, right? Another time they digested the sugars, then they digested the nucleic acid, and RNA, DNA, and then they found out that okay, only when you digest DNA, right, the transformation doesn't take place. And if the transformation doesn't take place, so that means DNA is essential for transformation. But then it is like kind of negative result, right? So you require conclusive experiment on it, and that is being provided by Hershey and Chase. Right? Hershey and Chase show that beyond doubt now that with a radio labeled tracer that the experiment showed that DNA is the genetic. Clear? Right? So now by this is like in 1953-54, right? This experiment came up, and then that is where it was showed beyond doubt that it is being DNA being the genetic. Now of course like people are like looking towards DNA very keenly, like they are like started working on DNA, right? Then of course like they learn many things about DNA down the line, and then what we are right? But then as you know, transformation, and this is transduction, right? We will study transformation and transduction down the line also, but then what Griffith showed is a transformation. Transformation means uptake of DNA from the environment, right? Transduction means what? A virus-mediated transfer of DNA, right? So this is a transduction-based experiment, and the Griffith's experiment was transformation-based experiment, right? But both experiments, right, beyond doubt showed that DNA is the genetic. Clear? This is experimental proof. Yesterday also I stressed an importance on being an experimental proof, right? So experimental proof is when you can repeat these experiments and then show beyond doubt, right, across the boundaries, into the different lab. There has to be reproducibility, and you could show reproducibly that this works, right? That is reproducibly shown that DNA is the genetic, right? So now we go ahead and then find out how this DNA is, what its function is, and what really it does inside this cell, right? So in next lectures or series of lectures that we will speak on DNA, right? On there, of course, like DNA structure is like known to you, like you've been studying from its standard and onward. So I won't give much importance to that, but of course, like I will tell you the key important parts of DNA, right? And then of course, like we will move on to show the function of DNA, because that is something really important part for us into the development. Okay, right?